So far this semester, we've done a few things. All right, we've taken all the things we learned in Physics 323 about bases and how quantum systems work, and the position representation and wave functions, and that we've applied them to a few systems, including the harmonic oscillator potential. Um, Looking at that, we introduced sort of an operator method with raising and lowering operators, with um, on how to treat that system. We also looked at the hydrogen atom, and solved the energy eigenvalue equation for that, figured out the energy eigenfunctions, and the energy eigenvalues. And then we looked at, more recently, we've looked at perturbation theory, which is sort of a technique we can use to look at a little more complicated systems, things that we can't solve exactly by basic or small additions to some of our exactly solved systems. Um, what we're going to do next is we're going to kind of take a closer look at the hydrogen atom, and look at some more, I guess, add some more detail to that to get a better representation. And we're going to look at what's called the hyperfine interaction. Um, this is essentially, if you look at the energy spectra of hydrogen, when we did our first sort of run through of the hydrogen atom, we looked at what we saw was that the energy levels depended on the principal quantum number n, and they're splitting when as 1/n². But if you actually measure the hydrogen atom, what you'll see is some splittings and some deviations from that 1/n² sort of energy levels. One of them is what we call the hyperfine interaction. And that's what we're going to start looking at today. It's going to lead into sort of a more proper treatment of angular momentum in quantum systems. And we're going to go from there. So what is the hyperfine interaction? Well, if we think back to when we first started looking at the hydrogen atom, we had a Hamiltonian that was essentially just the kinetic energy squared plus that Coulomb potential. We only looked at that electrostatic interaction between the positive charge in the nucleus and the negative charge on the electron. It turns out there are several more ways that electron and the two charges in that can interact with each other. The hyperfine interaction is dominated essentially by the magnetic moments of that nucleus and the electron, and how those magnetic moments interact. So if you recall, an electron with its spin has a magnetic moment that is negative g e charge of the electron over 2 mass of the electron times that spin angular momentum, or written in perhaps a simpler form, um, this negative GE times the Bohr magneton times the spin angular momentum over h bar. With the electron, GE is, just to remember, essentially 2. The proton, or the proton that makes up the nucleus in hydrogen, has its own magnetic moment based on its spin, and it has sort of an analogous uh, magnetic moment where it's the mass of the proton and the g factor of the proton, and we're going to use I for the spin of that proton, or written another way, g of the nucleus, um, mu of the nucleus times I over h bar. Right. In for the proton, uh, I've kind of gotten sloppy here with p's and n's, um, but the g factor is 5.59 about. And also note that the one of the major differences here is the mass of the electron. So the magnetic moment, because the protons, thousands, very much heavier than the electron, the magnetic moment of the nucleus, or the proton, is much smaller. Um, so if we take into account that these two, the things that make up our hydrogen atom have these magnetic moments, we can start to ask, well, how do magnetic moments interact with each other, and how is that going to change our system? To look at how that interaction is going to affect things, we have to sort of look at the magnetic field uh, from one of those dipoles, and how the other dipole's energy is sort of affected by it, right? So if we look at, say, the magnetic field from the nuclear dipole, um, we're not going to derive this now. That's should likely go through this in your E&M class, but it ends up being equal to this. R hat, the plus 2 mu naught over 3. So the that's an R. The magnetic field for, say, the nuclear dipole, which is located at, we'll call it what we're defining as the origin, is equal to this, the magnetic moment dotted with the R hat vector. Um, this is what the magnetic field of that dipole is. Similarly, we could also look at the magnetic field from the electron's dipole moment, magnetic dipole, and we get a similar form. But the gist is, this is the magnetic field from the the nucleus at the origin. And if we want to know the energy, how this affects the energy, well, the interaction energy of a dipole moment in the magnetic field from the other dipole moment is just the magnetic moment of particle 1 dotted with the magnetic field from the other particle. So if we look at this, we're just going to take, that dot product and put it together. This sort of magnetic field, the first term is sort of describes the magnetic field at some distance r, right? Your electron is away from the nuclear or the proton, and that's what the magnetic field that it experiences. This term with the delta function sort of describes the magnetic field when when that electron's at the origin, at the same place that that proton is. If you want to read more on this, the book doesn't actually go into much of this interaction. There is a paper from a while back, DJ Griffiths, in the American Journal of Physics, so just AMJ Phys, 50, you want the full reference, 5698. It's from 1982. This, if you want to read this, it goes through the hyperfine interaction problem for, a nice approach to it. But it goes into a little more detail about the actual electrodynamics, the interactions there, and where this Hamiltonian comes from. So if you're looking for a bit more info, you can look that up. If you can't find it in the library or online, feel free to email me and ask me about it. I can get you, point you to a copy. Anyway, sorry. So basically, we have to look at this magnetic field, dot it with our electron's magnetic moment, and we end up with the hyperfine interaction Hamiltonian, which will look like this when all's said and done. All right, so this is our hyperfine interaction Hamiltonian. It's got 3 terms, right? So we've got this first term here, our second term, and this Hamiltonian here, and then this third term over here. And they all sort of correspond to different aspects of the electron's magnetic moment interacting with the nuclear magnetic moments. And the gist is this first one here. You can see it has the intrinsic magnetic moment of the proton or our nucleus, and the orbital angular momentum of our electron. So it's that you can think of an electron in an orbit has, think of it classically kind of like a moving charge that's going to create a current and have a magnetic moment. That orbital magnetic moment, or that orbital angular momentum, interacts with the field from the magnetic field of the nucleus, and that leads to a change in energy. So that's the effect that relates to the orbital magnetic moment. This second term is related to the uh, intrinsic magnetic moments of those two particles, right? It has the intrinsic sort of spin, the magnetic moments related to the spin of those two particles, which have nothing to do with the orbits or which state they're in. They're just intrinsic properties of those particles. And so this is how those two are interacting. And this term is for when they're not at the same place, right? They're at this is when the electron is away from the nucleus, where their wave functions aren't overlapping. This third term is the same interaction. It involves the intrinsic spins or intrinsic magnetic moments of that electron and the proton, but for where they overlap, where that electron wave function is overlapping with the nuclear wave function. And that's why this is often referred to as the sort of the contact term. It's where the electron and the proton are in contact with each other and how those magnetic moments interact there. If we simplify all this and put it more in terms of our angular momentum operators, our spin operators, this ends up this can be written like this. Our hyperfine Hamiltonian can be written of a bunch of stuff comes out. GE mu Bohr-Mutington, nuclear G factor times that all over 4 pi h bar squared, and then we have 1 over r cubed, the nuclear spin operator dotted with the orbital angular momentum operator of that electron, minus 1 over r cubed, the electron spin operator dotted with the nuclear spin operator, plus 3 over r to the 5th, spin operator dotted with r, nuclear spin operator dotted with r, and then 8 pi over 3 electron spin operator dotted with the nuclear spin operator delta r, right? And this is what our hyperfine interaction term looks like. And now that we have that Hamiltonian, we can look at what it's going to do to our system. The way we're going to look at it is, we're looking for these sort of corrections or how the energy levels change. So we're going to use a perturbation theory, right? And we're looking for essentially the first order corrections to our energy level and how that works. And perturbation theory just told us that those were the diagonal elements of our perturbation Hamiltonian, which in this case is our hyperfine Hamiltonian. And for our unperturbed states, which are the hydrogen energy eigenfunctions, these are the elements we're looking for. So if we want to look at, how does this affect the n=1 state of hydrogen, we're going to be looking at how this 1, 0, 0 hydrogen state, we're going to be looking for that matrix element of our perturbation Hamiltonian, where that's our perturbation Hamiltonian. If we're focusing on that n=1 state, we can sort of quickly see, that if we take that 1, 0, 0 state, I dot L operating on that 1, 0, 0 state, well, we know if we look at the L squared, that angular momentum operator on the 1, 0, 0 state, it has that eigenvalue equation h bar squared L plus 1 times 1, 0, 0. So this L, the magnitude squared of that operator, L is 0 for this n=1 state. So this orbital angular momentum has 0 magnitude. For any L = 0 state, this first term is going to be 0. This first term is going to be 0 for any L = 0 state. You can sort of quickly see that. So we don't have to worry about that term for this in this diagonal element here. We can also sort of make similar. We can make arguments for why these second terms are going to be 0 as well. if we think of those terms, right? So we have the first term that goes proportional to uh, oops, the first one of those is going to be 1 over R3 S dot I. And the second one, and if we look at that, well, S and I, these spin operators, they correspond to the intrinsic spins of the electron and the proton. Those don't change. Those are intrinsic properties. They don't change based on where you are in R and R. So those are going to be sort of even about the origin, right? This R cube term is odd about the origin. And if we're looking at these wave functions, right, and we were actually to convert this matrix element into that integral over all space, and this is going to involve sort of the magnitude of that 1, 0, 0 wave function squared. These are going to be even as well, so we have a bunch of even terms in this integral, and this odd one. If we integrate over all space to get that matrix element, those are going to go to 0 as well. It's a little hand wavy, but hopefully you followed it. The same thing goes for this term as well, right? The spin and the spin of the electron and the proton are both intrinsic, so those are going to be even. Likewise here. So again, the parity of these wave functions was determined by that L. So if L, basically, if we have sorry, got tongue tied there. The gist is this 1 over R cubed term and the 1 over R to the 5th term here, these odd things, are going to make these integrals go to 0 as well, because when we integrate over all space and it's odd, those get 0. So essentially, the thing we're going to be concerned with to figure out this hyperfine interaction is this last, what we call the contact term. How the intrinsic spins, or the magnetic moments due to the intrinsic spins of the electron and the nucleus, or the proton that makes up the nucleus, how that interaction affects the energy when they're in contact with each other, when the wave function of the electron is overlapping with that of the proton. So what that means is the real sort of hyperfine, the non-zero hyperfine terms, when we're looking at that 1s, or the n equals 1 state, or really any L equals 0 state, we have the hyperfine, the perturbation Hamiltonian is going to be mu naught over 4 pi, those G factors, the Bohr magneton, oops, forgot it, nuclear G, mu n over h bar squared, 8 pi over 3, the dot product of those two spin operators, delta R, right? So we're looking, yeah. So this, and to figure out the first order energy correction, we're just going to look for the diagonal element of that perturbation Hamiltonian. This, doing so actually, though, gets a little trickier than what we might have seen. There's a subtlety here, right? If we look at this perturbation Hamiltonian, we can sort of see that, all right, these S dot I operators, well, they're spin operators, right? They're affecting, that spin up, spin down properties of our electron and our proton, whereas this part of this Hamiltonian is, it's a position type thing. It's affecting the position representation. It has to do with where the thing is in space, right? So there's sort of, these operate on different subspaces, right? And if we think about these, energy eigenfunctions we're looking at, those are position space wave functions. Nothing in here has anything to do with the spin. So we're kind of, how do we deal with that? And it turns out, the formal way of doing this is you have to define the larger subspace that includes the spin space and the position space, and you do that with tensor products and such. Beyond the scope of the course, but we can sort of, see how this works by considering, we're going to have some spin eigenbases or sorry, not spin eigenbases. We're going to have some spin related state function and some space uh, type function, and the full sort of state. So if we were to look at the full ket for our that describes our system, that ket, if you think way back to how we define these states, we said that the state ket defines everything we can sort of know about our quantum system. In this case, we can know spin properties and position properties, so the full ket will involve both of those. And it defines a larger Hilbert space there. We need to fill those things out, right? And excuse me. So when we do that for this hydrogen, uh, this 100 state, we're going to have this diagonal element is we'll just get rid of all the um, you know I'm going to just write it like this to keep track of what we are. This is going to come out, all these constants can come out front, or pi GE B GN UN for H bar squared, 8 pi over 3. But then we're going to have, our space sort of Bras and Ketz working on the space, the position part of our wave function, and the ket, the spin space, the spin part of our kets are going to be what the spin operators act on. And we can discuss this more in class. There's different, there's a few ways to think about it. It does get confusing. It has to do with the formal way involves tensor products and that, which we're not going to get into. But the gist is, hopefully you can accept this, is that we need to know how this Hamiltonian affects things, and it operates on spin and position subspaces. So we need to include both of those when we do our matrix element. This space sort of part of this matrix element is just, it's how we would do it. We integrate the wave function for the 100, that complex conjugate, times that operator, R, and the 100, sorry, operator on that dv. This delta function, brings that out. So essentially, this is just the probability density of our energy eigenfunction evaluated at r equals 0, at that origin, right? Because we're looking at that delta function. And we did this when we did the normalization and all that, but essentially we know our n equals 1 wave function is just 1 over root pi 1 over a naught to the 3 halves e to the negative r over 2 a naught. All squared. If we do this sort of full integral, we end up with, this is just 1 over pi a naught cubed, right? When we do it at r equals 0. So we figured out, the space part of this matrix element. The only thing we have left to do is consider the spin part over here. So where does that put us, right? So if we take, if we just add this to these group of constants here, we'll call that whole thing A, right? We have our hyperfine interaction, can be written as just A over h bar squared s dot I, where s and I are the spin operators for the electron and the nucleus. And again, after you simplify things, we've defined A as 2 over 3 pi a naught cubed, the g factor of the electron times the Bohr magneton times the g factor of the nucleus times the mu sub n. And this is our hyperfine Hamiltonian, the contact term in that, which is the only one that holds out whenever you have an L equals 0 state. if you think about this, what this is doing is if you have some, use some classical intuition with this, if you have two magnetic moments, they tend to align and lower their energy. Um, so if you have, the mu, the magnetic moment of that electron is proportional to negative sort of the spin angular momentum vector. So, and whereas the nuclear one is just proportional to its moment. So S dot I is going to be -1 when they're aligned, when the moments are aligned, which is anti-aligned spin. So that's going to lower the energy. The other way, it's going to raise it. But essentially, this is how we're going to take into account. We're going to use perturbation theory on this Hamiltonian and look at how that's going to perturb or change those unperturbed or simple energy, hydrogen energy eigenfunctions that we derived when we were looking at that atom. We're going to put that off until the next video. Essentially, next step is we've got two angular momentum sort of properties here, the spin of the electron, spin of the nucleus. We're going to have to look and recall a bit of how we think about angular momentum, use that to tackle this perturbation, and then eventually get to how the hyperfine affects our energy levels in the hydrogen atom. If you have any questions, bring them up in the synchronous sessions, email me. Yeah, this video, essentially all we did is point out that we're way back up here. When we looked at the hydrogen atom the first time around, we took sort of a pretty simple model of it, where the only interaction we cared about was that Coulomb interaction between the electron and the proton, or the nucleus. If we consider the fact that both the electron and the nucleus have magnetic moments, and the magnetic field due to those magnetic moments, we can see that another way that these another interaction that's going to affect our energy levels is this magnetic dipole interaction, which leads to this hyperfine Hamiltonian. If we're looking at the n equals 1 states, or really any L equals 0 state, a lot of those terms in that Hamiltonian go away, and we're left with just this hyperfine the contact hyperfine term here. And that can sort of be simplified once you take care of the space or position part of that Hamiltonian into this perturbation Hamiltonian, which we are going to attack and sort out in the next few videos, after we look at angular momentum and how to deal with that. I will see you in our synchronous sessions.